Okay, thank you, Mark, and thank you very much to the organizers for inviting me, and very happy to be here. And today I will shortly illustrate what we are doing in the use case team of the QIA project. So I will give a short overview of our activity and of the use cases. Yeah, sorry. So first of all, very shortly, Quantum Internet Alliance is a European project funded by the Quantum Flagship, Horizon Europe, and there is this FPA, which is a large consortium with 42 partners in 9 European countries. There are 2 phases. One is ongoing and will end next year, and then there is the second phase starting next year. What are the goals of this project? So the idea is to build a fully programmable quantum network, and the prototype that we will prepare for 2029 is a quantum network with 2 metropolitan scale networks connected by a long distance backbone, fiber backbone, with quantum repeaters to provide entanglement over this long distance. And we will show the implementation of 2 test protocols. One is deterministic teleportation, the other one is blind quantum computation. But very importantly, besides this technology that we have to develop, we want to create an European platform for quantum internet development. So there is a huge effort on hardware and software, and also in defining an architecture that can be a reference in Europe and worldwide. Then, in this big project, there is a use case team that I am leading since 1 year, about. The team includes several partners, so VeriCloud, Surf, University Berlin, Parma, which is my university, Dresden, INRIA, Sorbonne, CNRS, Portuguese Quantum Institute, and finally TU Delft and QTech. What we do is design use cases, trying to involve stakeholders, simulate use cases, because we want to assess these use cases from the quantitative point of view, not just qualitative. And to do this simulation, we use QIA tools and models. And another important activity is the use case outreach. So today, for example, is a opportunity to have this activity. Okay. How we characterize the use cases by means of this template for which we have a description of the use case, and we want to be clear in what is the quantum advantage. So if there is no clear quantum advantage, the use case is not interesting. The application area, the functionalities that the quantum network must provide to implement the use case, broadly speaking, the use domain, and then which protocols, quantum protocols are necessary. And we have as a reference this scheme for the network stage. So starting from something that is already ongoing, like trusted repeater, we want to reach the entanglement generation level with the project, but also go in the direction of quantum memory, few qubit fault tolerant, and finally quantum computing is the final goal that is to have quantum computers with error correction connected by a quantum network. So with this reference scheme, we also can say to which stage the use case refers. So what is the technology required to implement the use case? And finally, qualitative and quantitative assessment. So qualitative may be like why this use case is interesting, what are the target users, is a broad community or a small community. So, and quantitative assessment is by means, for example, of simulations, and later with also experimentation, try to assess what are the quantum resources that are necessary to implement the use case and having the use case that work correctly. Some examples have been recently published on the website of the project, so you can use this QR code to look at the description of these use cases. You can see these are 10 use cases, but we have more that we are studying. These 10 are quite different. So we have, for example, the document deletion from a system like Doctolib. Just an example, in France should be well known, but also in other states. It is a system in which you can share with doctors medical data, but at some point you want to be sure that they are deleted from the system if you don't want to share them no more. So classically you don't have a way to ensure these because these data are in cloud and you have to trust the cloud provider. When you delete. Then other use cases like clock synchronization or secure position verification. We have just seen a nice presentation on this topic. Quantum enhanced SDN management, which is a use case which is very interesting for network providers. So I will spend a few words later with the next slides on this. One-time proxy voting, multi-party entanglement for secure distributed function estimation. All these use cases have a security aspect, much or less emphasized or much or less important, but typically the quantum advantage is also having security, improved security, or security that cannot be provided using only classical protocols. Optical interferometry, small K referendum, quantum whistleblowing, and also quantum enhanced load balancing. So since I don't have a lot of time, I can just show you two examples. One is this quantum enhanced SDN management, control and orchestration, which was, the problem was provided by TIM, which is the major network operator in Italy. And we at the University of Parma are trying to help solving the problem, which is in a network that is managed by these distributed SDN controllers, which are basically software system that each of one controls a section of the network, so a subnetwork of a larger network. These SDN controllers sometimes have to elect one leader, decide one controller that performs some critical actions that have an impact on the whole network performance and reliability. So it is very important that the leader, there is just one leader when it is necessary, and that all SDN controllers agree on the leader. And the protocol for electing the leader should be robust in case of malfunctioning nodes, and also fair, which means that these controllers should have the same probability of being elected, at least those that are working correctly, independently, possibly, of the number of malfunctioning nodes. So there are several classical approaches to this problem, but no one of them has all the features that I just listed. So TIM, of course, is already using some distributed algorithm to solve this problem, but they are interested in having something that solve also other sub-problems that are not yet solved. So we have investigated the literature on quantum leader election, and we have found different algorithms that have different requirements. Currently, we are simulating an approach that requires entanglement generation, and entanglement is used by the controllers to perform a tournament for which they play in pair using entangled pairs to decide the winner of each game, and then they play a tournament until they get a winner, which is the leader. And of course, they have to also use classical strategies to organize this tournament, which are not trivial, but using the entanglement generation, at least they have a reasonable security that this protocol is fair. There are more complex protocols that requires up to the quantum computing stage of the network. They are even more robust, but they are so complicated right now that cannot be simulated. So we have to wait to have the real quantum systems to test these protocols. So this is one use case. The context, of course, is telecom, but the impact is all on the working of big, huge networks. So the end users are impacted by this kind of problem if it is not solved correctly. Another example is quantum whistleblowing, which is actually studied by the Technical University of Berlin. Here, the idea, the problem is providing a platform for whistleblowing, which means sharing anonymously information to report on, for example, unsafe working environment or any issue that can come out in a large group of users, and by preserving anonymity. So classical whistleblowing platform, again, have not all the features of truly anonymity that we would like to have. While there are quantum protocols like quantum anonymous transmission or secure anonymous conference in quantum networks that require entanglement generation, quantum memories, and the capability of distributing entangled states like GHZ states, which are large entangled states that are very, very powerful, meaning that they enable many interesting protocols like those one. So this kind of use case has a direct impact on, this kind of problem and solution have a direct impact on society, governance, so very different from the previous one, and but still very quite challenging to implement, but very interesting to study and to demonstrate. Okay, so with this one I've concluded, and thank you very much. And if you have questions, please.
You said several things that they're impossible, but so classically. Mm-hmm. But using protocol crypto, any of these are possible.
Okay.
Possible, you mean some information theoretic security guarantees?
Yes. Okay. We started from this kind of analysis, so the theoretical, and for example, quantum protocol Zoo was a very, very good reference for that, and all the teams that are working on the technical part of this protocol are first of all studying the possibility of having security proof like those that you illustrated in the preview. And for example, in the quantum leader election, there are protocols like those that I said we cannot simulate right now because they require quantum computation and they are quite complex also in theory, but they are very, very robust, and they have been proven to be secure in terms of having a secure proof of their effectiveness, robustness, and fairness.
I just think we have to be very careful in phrasing what the advantages are of these quantum protocols.
Yeah,
compared to the best possible solution of the classical.
Yeah, that's true. Of course, in one slide,
that doesn't land well with classical.
Yeah. Of course. Yeah, summarizing in one slide is very difficult, but of course we are working on technical reports with all these kind of analysis, and we clearly define what are the assumptions and what are the objectives. So if we want this fair quantum leader election, independent on the number of malfunctioning nodes, it is a very strong requirement, very, very difficult requirement. And in this case, the classical solution have been proven to provide fairness, but with a percentage of failing nodes that is limited, not any percentage. So in this case, there is a quantum advantage. But for the specific use case, for example, we are not considering malicious nodes, so nodes that act trying to misbehave. They misbehave because they want to. We are considering malfunctioning nodes, which is the realistic case in a SDN environment for telecommunication. So this is another kind of assumption that we have very clearly stated.
Can you define fairness in this context?
Yeah, fairness in this context is that the nodes that are working correctly have the same probability of being elected, considering the total number of nodes. So if there are n SDN controllers, the probability of being elected is 1 over n. So those that they should have if all are working correctly, and yeah, the objective is to have this because we want to have load balancing. I forgot probably to say. We don't want that there is one controller that is always doing all this work. That we want to have this, yeah. Which could be achieved with a round robin if they were all working correctly, but if they don't, you cannot have round robin working correctly.
Thank you.
Welcome.
Thanks a lot.
Well, thank you.